Hi, this is Mike Mayerhofer, Director of Technology at Liberty. Today I'm going to talk about using neural networks to optimize Midland Basin completions. First, the data set we're looking at is in the Permian Basin, specifically in the Midland Basin, looking at the Wolfcamp D formation. Our data set includes about 2,300 horizontal wells. You see a map on the right showing bubble size as the production, 1 year oil production of each of these wells, and the background is a TVD contour. In our statistical model, we used a total of 66 completion and reservoir geology parameters, and our response variable is the normalized 1 year oil production. So when we're doing complex statistical models, it's very important to do some data pre-processing and exploratory analyses. And this is what you see here briefly shown, is we need to identify what we call influential points, points that could really affect the statistical model and bias it in a certain direction. So, for example, what we do here is the pounds per foot on the left, you see a histogram of the distribution of that parameter. We will look for points that are way outside the distribution, and those will need to be eliminated. And then with recursive feature eliminations, in this particular project, we were able to obtain 8 variables that we had to select for the final modeling. So here you see the neural network training and testing. On the y-axis is the predicted oil production, the x-axis shows the observed oil production, and you can see quite a bit of scatter, but the neural network model is pretty good in terms of predictions. We have an R-squared of about 0.71, and more importantly, the root mean squared error is about 3 barrels per foot, which is pretty low. And also the test RMSE is only slightly higher than the training, which indicates that we have a model that's not significantly overfitting the data. So we also did a comparison of our neural network on the left with a previous model that we had done for the Midland Basin, and you can see that the neural network outperforms or is a slightly better statistical model than what we call the ACE physics-based model. So our squared is about 0.1 higher, and also the root mean squared error is also lower in the neural network. But more importantly, we use these statistical models to be predictive, and that's what you see on the right-hand side. You see the 1 year oil production over the proppant mass, and the dots are the actual observed production data, which is of course a big scatter because it's across the whole Midland Basin with all sorts of well performance. But the models are actually the blue curve, which is the ACE physics-based model, and the red curve, which is the neural network. And you can see differences there, and that's important. The blue curve, shows continuously decreasing or diminishing returns in the prediction, whereas the red neural network curve shows a more steeper incline between 1,000 and 2,000 pounds per foot. That's an indication you're getting more incremental oil per incremental proppant mass. That has important implications for the economic optimization, which you see here. So well cost on top, in the middle you see the cum oil prediction of the statistical model, and then on the bottom, most importantly, the dollar per BO that we're trying to optimize. And what you can see here is on the left, the neural network, because of that steeper increase in incremental oil production versus proppant mass, it tends to predict larger proppant mass as the optimum. In this case, a little over 3,000 pounds per foot with slick water jobs, whereas the previous model, the ACE physics-based model, points to a lower optimum proppant mass of only about 1,200 pounds per foot. So you can see here, depending on which statistical model you use, you can get vastly different answers. We feel like that the neural network is at this point a better predictor because for a parent well in the Midland Basin, when you're pumping local sand, the bigger jobs are probably going to be the better option. However, if you start infilling wells, you may probably want to go more to the lower proppant mass that the ACE physics-based model is predicting at this point. But this model will be updated also with infill drilling data, and so these results may change after that. As always, if you need more detailed information about our processes, please contact us at libertyfrac.com. Thank you.